Right now, something unimaginable is coming for us. Not an asteroid, not a comet. An entire galaxy, Andromeda, a trillion stars strong, is falling straight toward the Milky Way. In 4 billion years it arrive, and our night sky will never be the same again. Now, before you panic, let me be clear. This isn't the kind of collision you're thinking of. When two galaxies merge, it's nothing like two cars crashing. There won't be explosions or debris flying everywhere. In fact, if you were somehow alive to witness it, standing on Earth during the collision, you might not even notice anything dramatic happening in your lifetime. But over millions of years, everything we know about our galaxy, our night sky, and our cosmic neighborhood will be completely transformed. Tonight, we're going to explore what that collision will actually look like, how it begins, what happens to Earth, what becomes of our Sun, and what strange new galaxy emerges from the chaos. We'll walk through the entire process, from the first signs of approach to the final merged galaxy, billions of years later. And we'll do it in a way that makes sense, without the complicated jargon, just two friends talking about one of the most spectacular events that will ever happen in our cosmic backyard. So settle in. This is going to take a while, because this story spans billions of years and involves forces so massive they reshape entire galaxies. But by the end, you'll understand exactly what's coming and why astronomers are both fascinated and slightly awed by what our distant descendants might witness. Let's start with the basics, because before we can understand the collision, we need to understand what's actually going to collide. Our Milky Way is what astronomers call a barred spiral galaxy. Imagine a flat disk with spiral arms curving out from the center, kind of like a cosmic pinwheel. At the very center sits a bar-shaped structure made of densely packed stars, and at the heart of that bar is a supermassive black hole weighing about 4 million times what our Sun weighs. The whole thing is roughly 100,000 light-years across. That means if you could travel at the speed of light, it would take you 100,000 years just to cross from one edge to the other. The Milky Way contains somewhere between 100 and 400 billion stars. That's a huge range because it's actually really hard to count stars in your own galaxy when you're sitting inside it. It's like trying to count all the trees in a forest while standing in the middle of it. Everything nearby blocks your view of what's farther away. Now, Andromeda is similar but bigger. It's also a spiral galaxy, though its spiral arms are wound a bit tighter than ours. It contains roughly 1 trillion stars, maybe more. That's at least twice as many stars as the Milky Way, possibly 3 times as many. And it's about 220,000 light-years across, more than twice our diameter. If you could see Andromeda's full extent in our night sky, it would appear about 6 times wider than the full moon, even though it's 2.5 million light-years away. We can only see its bright central core with our naked eyes, which is why it looks like a fuzzy little smudge. Both galaxies have been around for a long time. The Milky Way formed about 13 billion years ago, not long after the Big Bang. Andromeda is roughly the same age. They've been neighbors in the same cosmic neighborhood called the local group for their entire existence. The local group is just a name for our little cluster of galaxies, which includes the Milky Way, Andromeda, and about 50 smaller galaxies, most of which are tiny dwarf galaxies orbiting around the 2 big ones like moons around planets. For most of their lives, the Milky Way and Andromeda have been slowly circling each other at a distance, held together by mutual gravity. But here's the thing about gravity. It never stops pulling. Over billions of years, that pull has been drawing them closer and closer together. And now, we're at a point where the collision is inevitable. Astronomers figured this out by measuring something called Andromeda's radial velocity. Basically, they looked at the light coming from Andromeda and checked for something called the Doppler shift. You know how an ambulance siren sounds higher pitched when it's coming toward you and lower pitched when it's moving away? light does the same thing. If a galaxy is moving toward us, its light shifts toward the blue end of the spectrum. If it's moving away, it shifts toward red. When astronomers measured Andromeda's light back in the early 2000s, they found it was blue shifted. That meant it was coming toward us. By measuring how much the light had shifted, they could calculate the speed. About 250,000 miles per hour, or roughly 110 kilometers per second. That might sound insanely fast, and it is by human standards. But in cosmic terms, where distances are measured in millions of light years, it's actually a pretty leisurely pace. The collision isn't going to happen tomorrow. Current estimates put it at roughly 4 to 4.5 billion years from now. That's about the same age as the Earth itself. So if Earth had a twin that was born today, by the time that twin planet was as old as Earth is now, the collision would just be starting. But here's something interesting. Even though the galaxies are approaching, the actual merger will take much longer than you'd think. When they finally meet, they won't just slam together and stick. Instead, they'll pass through each other, get pulled back together by gravity, pass through again, and repeat this dance several times over the course of about 2 billion years before they finally settle into a single merged galaxy. Think of it like dropping a ball into a bowl. The ball rolls down one side, up the other side, back down, back up, and eventually settles at the bottom. The Milky Way and Andromeda will do something similar, except the bowl is made of their combined gravitational field, and instead of a ball, you have two enormous collections of hundreds of billions of stars. Now, you might be wondering, why doesn't this happen faster? Why does it take billions of years for galaxies to merge? The answer has to do with the absolutely mind-boggling distances involved. Even though there are hundreds of billions of stars in each galaxy, the actual space between those stars is enormous. Our nearest star neighbor, Proxima Centauri, is about 4 light-years away. That's roughly 25 trillion miles. The distance between stars is so vast that when two galaxies merge, the stars themselves almost never actually hit each other. Let me give you an analogy. Imagine two swarms of bees flying toward each other. There are thousands of bees in each swarm, all buzzing around. When the swarms pass through each other, you'd expect lots of collisions, right? But now imagine each bee is the size of a grain of sand, and the space between bees is the size of a football field. Suddenly, the chances of any two bees actually hitting each other becomes incredibly small. That's what it's like when galaxies collide. The stars are so far apart that they just sail past each other. But even though the stars don't collide, their gravitational influence on each other is enormous. Every star pulls on every other star, and when you have hundreds of billions of stars all pulling in different directions, the result is chaos. The neat spiral structure gets scrambled. Stars get flung into new orbits. Some stars get ejected from the galaxies entirely, thrown out into intergalactic space. And the gas and dust between the stars, which is much more spread out and easier to disturb, gets compressed and heated, triggering massive bursts of new star formation. This is what makes galaxy mergers so spectacular. They don't destroy galaxies in the sense of blowing them apart. Instead, they transform them, reshaping the structure and creating conditions for a new generation of stars to be born. Let's talk about where we are right now in the present day. Andromeda is visible in our night sky, and it has been for as long as humans have existed. Ancient astronomers noticed it. The Persian astronomer Abd al-Rahman al-Sufi described it back in the year 964, calling it a small cloud. But nobody really understood what it was until the early 20th century. For a long time, people thought Andromeda was just a nebula, a cloud of gas within our own galaxy. It wasn't until the 1920s that astronomer Edwin Hubble proved it was actually another galaxy entirely, vastly distant from our own. He did this by identifying individual stars within Andromeda and measuring their brightness, which allowed him to calculate the distance. When he worked out the math, he realized Andromeda was nearly 1 million light-years away. We now know it's about 2.5 million light-years away, but even Hubble's rough estimate was enough to prove that it was far outside the Milky Way. That discovery fundamentally changed our understanding of the universe. Suddenly, the cosmos was much larger than anyone had imagined. Our galaxy wasn't the entire universe. It was just one island in an ocean of galaxies. Today, we can study Andromeda in incredible detail. We've mapped its structure, counted its stars, measured its mass, and tracked its motion. We know it has at least 14 satellite galaxies orbiting around it, small dwarf galaxies that are gravitationally bound to Andromeda, just like the Magellanic Clouds are bound to the Milky Way. We also know that Andromeda has had a violent past. Studies of its stellar populations suggest it's already absorbed several smaller galaxies over its lifetime. You can actually see evidence of this in the distribution of stars. There are streams and shells of stars in Andromeda's outer regions, the leftover remnants of dwarf galaxies that got too close and were torn apart by tidal forces. In a sense, Andromeda has been practicing for its merger with us. The Milky Way has a similar history. We've consumed dozens of smaller galaxies over our lifetime. The Sagittarius dwarf elliptical galaxy is currently being torn apart as we speak, its stars scattered in long streams that wrap completely around our galaxy. In a few billion years, there won't be a Sagittarius dwarf anymore. It'll be completely absorbed, its stars indistinguishable from the rest of the Milky Way. So both galaxies are experienced at this. The merger with each other will be different though, because this time we're dealing with two galaxies of comparable size. When a large galaxy eats a small one, the large galaxy barely notices. It's like an ocean absorbing a river, but when two large galaxies merge, it's more like two rivers of equal size joining together. Both are transformed in the process. Let's step back and ask a more fundamental question. Why do galaxies merge at all? What causes them to fall together? The simple answer is gravity. Gravity is always attractive, always pulling things together. Any two objects with mass will attract each other. The more massive the objects and the closer they are, the stronger the attraction. When the universe was young, it was filled with small clumps of dark matter and gas. These clumps attracted each other through gravity, gradually growing larger. Over hundreds of millions of years, they grew into the first galaxies. These early galaxies were small and chaotic, not at all like the neat spiral galaxies we see today. As the universe continued to expand and evolve, these small galaxies began to merge with each other. Larger galaxies formed from the merger of smaller ones. This process continued for billions of years, and it's still happening today. Most of the large galaxies we see, including the Milky Way and Andromeda, are the result of many smaller galaxies merging together over cosmic time. But here's where it gets interesting. The universe is expanding, and that expansion is accelerating. You'd think this would prevent galaxies from merging, right? If space itself is stretching, shouldn't galaxies be getting farther apart? That's true on large scales. Distant galaxies are indeed moving away from us, carried by the expansion of space. But on smaller scales, within galaxy groups and clusters, gravity can overcome the expansion. The local group is one of these regions. The Milky Way and Andromeda are close enough and massive enough that their mutual gravity is stronger than the expansion of space trying to push them apart. So they're falling together, and they have been for billions of years. Initially, they might have been moving apart with the expansion of the universe, but at some point, their mutual gravity took over and reversed their motion. Now, they're approaching each other, and that approach is accelerating as they get closer, and their gravitational pull on each other gets stronger. The timing of the collision depends on several factors. How fast are they approaching? What are their exact masses? What's the distribution of dark matter in their halos? Are there any smaller galaxies that might affect their trajectories? Astronomers have to account for all of these factors when they calculate when the collision will happen. The most recent studies, using data from the Hubble Space Telescope and the Gaia satellite, suggest the collision will begin in about 4 billion years. But there's some uncertainty in that number. It could be as soon as 3.5 billion years, or as late as 5 billion years. The exact timing depends on factors we're still working to measure precisely. So let's fast forward. It's 4 billion years from now, give or take a few 100 million years. By this time, Earth has changed dramatically, though not because of the approaching galaxy. The Sun has been slowly getting brighter and hotter throughout its life, and by now it's about 40% more luminous than it is today. This has made Earth considerably hotter. The oceans may have already started to evaporate, and if any life still exists on the surface, it's probably clinging to survival in the polar regions or deep underground. Humanity, if it still exists, has long since either evolved into something unrecognizable or left Earth altogether. Maybe we've colonized other planets in the solar system, or maybe we've built habitats in space. Or maybe we're extinct, having been replaced by whatever came after us, or having left no successor at all. For the purposes of this story, let's assume some form of intelligent life exists somewhere in the solar system, with telescopes and sensors capable of watching what's about to unfold. From Earth's perspective, or from wherever our descendants are watching, Andromeda has been getting steadily larger in the night sky for millions of years. Remember, today it looks like a small fuzzy patch. You can see it with your naked eye if you're in a dark location, but it's not particularly impressive. It's in the constellation Andromeda, hence the name, and it's been a fixture of the northern sky for as long as humans have been looking up. But now, 4 billion years later, it dominates the sky. Instead of a small smudge, it stretches across a significant portion of the heavens. Its spiral structure is clearly visible even without telescopes. You can see the bright central bulge, surrounded by the sweeping spiral arms dotted with bright blue regions where young, hot stars are forming. The entire galaxy has a faint glow from the billions of older, cooler stars that make up most of its mass. And it's growing larger every year. Not quickly enough to notice from one night to the next, but if you could compare the sky from one decade to the next, the difference would be obvious. Andromeda is getting closer. At this stage, even though the galaxies are still millions of light years apart, they're already beginning to influence each other. The gravitational pull between them is starting to distort their shapes. The Milky Way and Andromeda are both starting to develop tidal tails. Long streams of stars pulled out by the other galaxy's gravity. Think of it like how the moon pulls on Earth's oceans, creating tides. The same principle applies here, except instead of water, it's stars and gas being pulled. These tidal tails are the first visible sign that the merger has begun. They're not dramatic yet, just slight distortions in the outer edges of each galaxy. But they're growing, and over the next few 100 million years, they'll become more and more pronounced. Inside the Milky Way, things are still fairly normal. The Sun continues its orbit around the galactic center, taking about 225 million years to complete one loop. We're currently about 26,000 light-years from the center, in a relatively calm region between spiral arms. This region is sometimes called the Orion Spur or the local arm, and it's been a safe, stable place for the solar system to exist for the past 4.6 billion years. But that stability is about to change. As Andromeda draws closer, its gravitational influence begins to affect the orbits of stars throughout the Milky Way. The changes are subtle at first. A star's orbit might become slightly more elliptical, or its path might tilt a bit relative to the galactic plane. But these small changes add up over time, and as Andromeda gets closer, the disruptions become more severe. The gas clouds between the stars are affected even more dramatically. These clouds are much less dense than stars, so they respond more quickly to gravitational disturbances. As Andromeda's gravity pulls on the Milky Way's gas, it compresses some regions and stretches others. In the compressed regions, the gas becomes dense enough for gravity to take over, and new stars begin to form. This is the beginning of what astronomers call a starburst, a period of intense star formation triggered by the merger. Starbursts are common in colliding galaxies. When two galaxies interact, their gas clouds collide and compression leads to star formation. The result is that colliding galaxies often have much higher rates of star formation than isolated galaxies. From our vantage point, watching all this happen, we'd start to see new bright blue regions appearing throughout both galaxies. These are clusters of young, massive stars, the kind that burn hot and bright. They're short-lived by stellar standards, lasting only a few million years before exploding as supernovas, but they're incredibly luminous while they're around. Their formation is a clear sign that the merger is underway. Let's take a moment to understand what's actually happening when these tidal tails form. It's a beautiful example of how gravity works on cosmic scales. Gravity gets weaker with distance. The farther you are from a massive object, the less pull you feel. This is described by Newton's inverse square law. Double the distance and the gravitational force becomes 4 times weaker. Triple the distance and it becomes 9 times weaker. Now, imagine you're a star on the edge of the Milky Way that's closest to Andromeda. You feel a certain gravitational pull from Andromeda. But a star on the opposite edge of the Milky Way, the side farthest from Andromeda, is farther away and feels a weaker pull. This difference in gravitational force across the galaxy is what creates tidal forces. The stars closest to Andromeda get pulled harder than the stars farther away. This stretches the galaxy, elongating it toward Andromeda. At the same time, the stars on the far side, feeling less pull, start to lag behind. They form a tail stretching away from Andromeda. The same thing happens to Andromeda. It gets stretched by the Milky Way's gravity, forming its own tidal tails. As the galaxies approach, these tails grow longer and more prominent, eventually stretching for hundreds of thousands of light years. But here's something counterintuitive. The tidal tails don't point directly toward or away from the other galaxy. They curve, forming graceful arcs through space. This happens because the galaxies aren't just pulling on each other, they're also rotating. Each galaxy is spinning, completing one rotation every few 100 million years. As they pull on each other, the rotation causes the tidal tails to curve, like water spiraling down a drain. Computer simulations of galaxy mergers show these curved tidal tails forming naturally. The simulations track the motion of millions of particles, each one representing a clump of stars or dark matter, and calculate how gravity affects each particle's trajectory. When you run these simulations for billions of simulated years, you see the tidal tails emerge, grow, and eventually wrap around the merging galaxies in complex patterns. These simulations have been refined over decades. In the 1970s and 80s, astronomers ran simple simulations with just a few thousand particles. Today, with modern supercomputers, we can simulate mergers with billions of particles, tracking not just the stars, but also the gas and dark matter. These detailed simulations have taught us an enormous amount about how galaxy mergers work. Let's jump forward another few 100 million years. Andromeda now fills a huge portion of the sky. Its spiral arms are stretched and distorted, no longer the neat, organized structure they once were. The same is true for the Milky Way. Both galaxies have developed long tidal tails streaming out into space, each tail containing millions of stars pulled away from the main body of their parent galaxy. And now, finally, the outer edges of the two galaxies begin to overlap. This is first contact, the moment when stars from one galaxy actually enter the space occupied by the other galaxy. It's not a sharp boundary. Galaxies don't have edges like a table or a wall. They gradually fade out, becoming less and less dense until you can't really say where the galaxy ends and intergalactic space begins. But there's definitely a point where you can say the galaxies are now occupying the same space. What does this look like from Earth? Well, assuming Earth is still habitable, which is questionable at this point, the night sky would be absolutely spectacular. Instead of the faint Milky Way band we see today, you'd see two distinct structures crossing the sky. One would be the remaining core of the Milky Way, still recognizable but distorted. The other would be Andromeda's core, now so close that individual bright stars would be visible within it. Between the two cores, you'd see chaos. Stars from both galaxies would be mixed together, creating a complex, turbulent structure. Bright blue regions of star formation would dot the sky, looking like glowing clouds. And threading through everything would be dark lanes of dust, silhouetted against the background glow. But here's the remarkable thing. If you were standing on Earth at this moment, you probably wouldn't notice anything unusual in your daily life. The sky would look spectacular at night, sure, but during the day, the sun would still rise and set. The seasons would still change. Life, if any existed, would go on as normal. That's because even though the galaxies are colliding, the distances between individual stars are still enormous. The nearest stars from Andromeda are still many light years away. There's no immediate danger of a collision with another star. No radiation surge, no gravitational disruption of Earth's orbit, just a slowly changing night sky. However, not everything is calm. The galaxy as a whole is beginning to feel the effects. The sun's orbit around the galactic center, which has been stable for billions of years, is now changing. Andromeda's gravity is pulling on everything in the Milky Way, and the result is that orbits are becoming more chaotic. Some stars are being pulled toward Andromeda. Others are being flung outward, away from both galaxies. And some, including possibly our Sun, are simply having their orbits scrambled, sent into new paths that are more elliptical, more tilted, or more erratic than before. This orbital scrambling is one of the main effects of a galaxy merger. Before the collision, most stars in a spiral galaxy follow fairly circular orbits around the galactic center, all moving in roughly the same plane. This organized motion is what creates and maintains the spiral structure. But when you add the gravitational influence of another galaxy, that organization breaks down. Stars get kicked into new orbits that are more random, more three-dimensional. The neat flat disk puffs up into a more spherical shape. This is actually how elliptical galaxies form. When two spiral galaxies merge, the result is almost always an elliptical galaxy, a roughly sphere-shaped collection of stars with no spiral arms and no organized rotation. The stars are just moving in random directions, held together by their mutual gravity. It's like taking two orderly marching bands and having them walk through each other. Afterward, you don't have two marching bands anymore. You just have a crowd milling around. Now let's talk about what happens to individual star systems during this phase. We've established that direct collisions between stars are incredibly rare, but that doesn't mean star systems are unaffected. One of the biggest risks comes from the Oort cloud. This is a vast, spherical shell of icy bodies surrounding our solar system, extending about 1 light year from the Sun. These are comets, billions of them, leftovers from the formation of the solar system. They're barely held by the sun's gravity, sitting in a delicate balance. When another star passes relatively nearby, say within a few light years, its gravity can disturb these comets. Some get knocked into new orbits that send them plunging toward the inner solar system. This increases the rate of comet impacts on the planets, including Earth. Normally, the Oort cloud sends a few comets into the inner solar system every million years or so. But during a galaxy merger, when the density of nearby stars increases, this rate could go up significantly. Instead of a few comets per million years, you might see dozens or hundreds. For any planets with life, this could be catastrophic. A large comet impact can cause mass extinctions, destroy ecosystems, and fundamentally alter a planet's climate. This is actually one of the more plausible ways the merger could directly affect life. Not through stellar collisions, which are essentially impossible, but through an increased bombardment of comets stirred up by passing stars. There's also the issue of radiation. During the starburst phase, when massive stars are forming at an accelerated rate, the overall level of radiation in the galaxy increases. These massive stars emit intense ultraviolet radiation, and when they die, they explode as supernovas, releasing even more radiation in the form of X-rays and gamma rays. If a supernova occurs within a few dozen light years of Earth, it could be dangerous. The radiation could strip away part of our atmosphere, particularly the ozone layer that protects us from ultraviolet radiation. This could lead to increased surface radiation levels, potentially harmful to life. How likely is this? It depends on where we are in the galaxy and how close we are to regions of active star formation. If we happen to be near one of the compressed gas clouds where new stars are forming, the risk increases. If we're in a relatively empty region, we're probably safe. But remember, all of this is happening over millions of years. Even if the rate of supernovas increases tenfold during the merger, we're still talking about rare events spread across vast distances. The chance that any particular star system gets hit by a nearby supernova is still pretty low. Fast forward a few 100 million more years. The two galactic cores are now approaching each other for the first time. This is one of the most dramatic moments of the entire merger, though again, it happens over millions of years, so dramatic is relative. Each galaxy has a supermassive black hole at its center. The Milky Way's black hole, Sagittarius A star, weighs about 4 million solar masses. Andromeda's black hole is bigger, somewhere around 100 to 200 million solar masses. That's at least 25 times more massive than ours, possibly 50 times more massive, and now these two monsters are heading toward each other. As the cores approach, the density of stars increases dramatically. Near the center of each galaxy, stars are packed much more tightly than in the outer regions. In our solar neighborhood, the nearest star is about 4 light-years away. Near the galactic center, the average distance between stars might be just a few light weeks or even light days. And when two galactic centers pass through each other, you temporarily have double the density. This creates opportunities for close encounters between stars. While direct collisions are still rare, stars can pass close enough to each other that their gravitational influence becomes significant. A star might have its orbit drastically altered by a close pass with another star. Or, if a star has planets, those planets might be disturbed or even stripped away by the gravity of a passing star. For our solar system, this is one of the most dangerous moments of the entire merger. If we're unlucky enough to be near the cores during this passage, there's a small but real chance that a close encounter with another star could disrupt the orbits of the planets. Jupiter might be knocked into a different orbit. Earth might be pushed closer to the Sun or farther away. In a worst-case scenario, Earth could be ejected from the solar system entirely, sent wandering into interstellar space. But let's put that risk in perspective. Even in the dense environment near the galactic cores, the chances of any individual star having a disruptive close encounter are pretty low. Most stars, including probably the Sun, will pass through this period without any direct interactions. The distances are still just too large. What's more likely to affect us is the indirect effects. The gravitational chaos of the merger will send ripples through the entire galaxy. These ripples can disturb the orbits of everything, not just stars but also the gas clouds and the dark matter that makes up most of the galaxy's mass. And these disturbances can trigger events far from the cores. The density of the galactic core during this passage would be something to behold. If you could somehow watch from a safe distance, you'd see two bright, compact regions of stars approaching each other, each surrounded by a haze of gas and dust. As they pass through each other, the gravitational interactions would cause the gas to heat up dramatically, glowing in X-rays and ultraviolet light. Some of this gas would fall toward the supermassive black holes, feeding them and causing them to become temporarily more active. When a black hole feeds, it doesn't just swallow material silently. The infalling matter forms an accretion disk, a swirling disk of superheated gas orbiting the black hole at nearly the speed of light. This disk can outshine the entire galaxy, radiating enormous amounts of energy. If both black holes become active during the core passage, the centers of both galaxies would light up brilliantly. From a distance, you'd see two intensely bright points of light, like cosmic headlights, rushing toward each other. This would be a spectacular sight for any observers in nearby galaxies. Now let's talk about what happens to the supermassive black holes. This is one of the most fascinating parts of the merger, and it's something astronomers are really interested in because we've never actually observed it happening in detail. When the two galactic cores pass through each other for the first time, the black holes don't immediately merge. They're still millions of light years apart in their first passage, separated by all the stars and gas between them. But as the galaxies swing back together for subsequent passages, the black holes get closer and closer. Eventually, they end up orbiting each other. Two supermassive black holes, one weighing 4 million suns and the other weighing perhaps 100 million suns, circling around their common center of mass. This is called a binary black hole system, and it's an incredibly powerful source of gravitational waves. Gravitational waves are ripples in space-time itself, created by accelerating massive objects. They were predicted by Einstein over 100 years ago, but weren't directly detected until 2015, when scientists observed the merger of two much smaller black holes. Since then, we've detected gravitational waves from dozens of black hole mergers, but all of them involved stellar mass black holes, the kind that form when massive stars die. We haven't yet detected the merger of two supermassive black holes, but we know it must happen during galaxy mergers. When Sagittarius A star and Andromeda's black hole finally orbit each other closely, they'll emit gravitational waves at a low frequency, lower than what our current detectors can sense. Future space-based detectors, like the planned LISA mission, should be able to detect these waves. If there are any civilizations in the local group with advanced enough technology, they'll be able to observe this event in gravitational waves, watching as the two black holes spiral together. The orbital period gets shorter and shorter as the black holes lose energy to gravitational waves. They might orbit each other for millions of years, but eventually they get close enough that the orbital period drops to hours, then minutes, then seconds. And then, finally, they merge. The merger itself happens incredibly quickly. Two black holes, orbiting each other at a significant fraction of the speed of light, suddenly combine into a single, larger black hole. The new black hole will weigh about 104 million solar masses, the sum of the two original black holes. In the process, some mass gets converted directly into energy in the form of gravitational waves. It's the most powerful event in the universe except for the Big Bang itself. The amount of energy released in just a few seconds is more than all the stars in both galaxies combined will emit over millions of years. But here's the thing, that energy is emitted as gravitational waves, not light. So unless you have a gravitational wave detector, you won't see anything. The night sky won't suddenly light up. There won't be a visible explosion. The black holes will just quietly merge, shaking the fabric of space-time, but not creating any visible display. After the merger, the new black hole will likely receive a kick, a recoil effect from the asymmetric emission of gravitational waves. This kick can be powerful enough to send the black hole moving through the galaxy at hundreds or even thousands of miles per second. Eventually, it will settle down at the center of the new merged galaxy, but for a while, it might wander. This wandering supermassive black hole is another potential hazard, though again, the chances of it coming anywhere near any individual star system are vanishingly small. Space is just too big. But if it did pass close to a star, it would be catastrophic. The black hole's immense gravity would tear the star apart, creating a spectacular tidal disruption event that would briefly outshine the entire galaxy. The kick velocity depends on the spins and masses of the two black holes. If they're spinning in the same direction and their spins are aligned, the kick is relatively small. If they're spinning in opposite directions or at odd angles, the kick can be much larger. Computer simulations suggest kicks of up to several thousand miles per second are possible. A black hole moving at these speeds would take millions of years to slow down and settle at the galactic center. During this time, it would plow through the galaxy, occasionally encountering stars and gas clouds. Any star that came too close would be captured or disrupted, adding to the black hole's mass. After the first passage, the two galaxies don't just stick together, they're moving too fast for that. Instead, they swing past each other, pulled apart by their own momentum, and then gradually slow down and swing back together for a second pass. This happens because they haven't lost enough energy yet. It's like those pendulum balls in a Newton's cradle. They swing back and forth several times before finally settling down. Each passage takes hundreds of millions of years. The galaxies swing out to enormous distances, tens of thousands of light years apart, and then slowly curve back together. And with each passage, they lose energy. How? Through what's called dynamical friction. Dynamical friction is a fancy term for a simple idea. As a massive object moves through a sea of smaller objects, it gravitationally pulls on them, and they pull back. This interaction slows the massive object down, converting its kinetic energy into random motion of the smaller objects. In the case of merging galaxies, the massive objects are the dense cores of each galaxy, and the smaller objects are the stars and dark matter in the outskirts. With each passage, dynamical friction saps energy from the galaxy's orbit, making their next swing less energetic. They don't fly apart as far, they come back together more quickly. And the encounters become more violent, with more gravitational disruption, more tidal stretching, more star formation. By the second or third pass, the galaxy's original structures are almost completely destroyed. The spiral arms are gone, shredded by tidal forces. Stars are scattered throughout a huge volume of space, their orbits randomized. The gas and dust have been compressed and heated in multiple rounds of collisions, triggering waves of star formation. The night sky, if anyone is still around to watch, would be a chaotic mess of bright stars, glowing gas clouds, and dark dust lanes, constantly changing as structures form and dissolve. During this phase, our solar system's fate becomes clearer. If we've made it this far without any close encounters, we're probably going to be okay. But our location in the final galaxy will be determined by chance and by the exact details of how the merger unfolds. Some stars get thrown into the outer reaches of the merging system, ending up in what will become the halo of the new galaxy. These stars will orbit the new galactic center at large distances, rarely coming close to the dense central regions. Other stars end up closer to the center in what will become the bulge of the new elliptical galaxy. And some stars, perhaps a few percent of the total, get ejected entirely, thrown out of the galaxy altogether into intergalactic space. If the Sun gets ejected, it will become what's called a rogue star, wandering through the vast emptiness between galaxies. Earth, if it's still bound to the Sun, will go with it. From Earth's perspective, the night sky would change dramatically. Instead of being inside a galaxy, surrounded by stars and the glow of the galactic plane, we'd be in darkness. The new merged galaxy would be visible as a bright smudge in the distance, slowly receding. And beyond that, just the distant points of light from other galaxies in the local group, and eventually, nothing but the cosmic microwave background, the faint glow left over from the Big Bang. But this is an unlikely fate. Most stars remain bound to the new galaxy. The Sun, if it survives as a star at all, will probably end up somewhere in the new galaxy's structure, possibly in the halo, possibly in the bulge, depending on the exact trajectory it follows during the merger. The multiple passages create a complex dance of gravitational interactions. Each time the cores pass through each other, they exchange energy and angular momentum. Stars and gas get sloshed back and forth, sometimes moving with one core, sometimes with the other, sometimes ending up in the tidal tails. This creates a thoroughly mixed population. By the time the merger is complete, stars from the Milky Way and Andromeda will be so intermingled that you won't be able to tell which galaxy they originally came from. They'll all just be part of the new galaxy. Throughout all of this, one of the most visible effects is the burst of star formation. Every time the galaxy's gas clouds collide and compress, new stars form. And because there are multiple passages, there are multiple waves of star formation, each one adding more young, hot, bright stars to the mix. These starburst periods can increase the rate of star formation by factors of 10 or even 100 compared to normal. Galaxies usually form stars at a fairly steady rate, converting a few solar masses of gas into stars every year. But during a starburst, that rate can jump to tens or hundreds of solar masses per year. The new stars are predominantly massive and hot. When gas clouds collapse to form stars, they form stars of all different masses, from small red dwarfs barely massive enough to fuse hydrogen, all the way up to massive blue giants weighing dozens or even over 100 times what the Sun weighs. But the massive stars are the ones you notice because they're so much brighter. A massive star can be tens of thousands or even hundreds of thousands of times more luminous than the Sun. They burn through their fuel incredibly quickly, living only a few million years before exploding as supernovas. But while they're around, they dominate the light output of the galaxy. This means that during the merger, both galaxies become much brighter, especially in blue light. If you could somehow watch from a distance, you'd see the two galaxies grow brighter as they approach, brightest during and shortly after each close passage, and then gradually fading as the burst of star formation dies down, only to brighten again during the next passage. These massive stars also have a huge impact on their surroundings. They emit intense ultraviolet radiation that heats and ionizes the gas around them, creating glowing nebulas. They have powerful stellar winds that blow material away, clearing out bubbles in the gas clouds. And when they finally die in supernova explosions, they inject enormous amounts of energy back into the interstellar medium, further heating and stirring the gas. This feedback from massive stars is actually what eventually shuts down the starburst. After enough supernovas have gone off, the gas becomes so hot and turbulent that it can no longer collapse to form new stars. The starburst ends and star formation drops back to a lower, more sustainable rate. For any planets in the vicinity of these starbursts, the environment becomes much harsher. The ultraviolet radiation from massive stars can strip away planetary atmospheres. Supernova explosions, if they occur close enough, can bathe planets in deadly radiation. This is another way the merger could affect life, not through direct collisions or gravitational disruptions, but through the increased radiation from all the new massive stars and their subsequent supernovas. On the other hand, this burst of star formation also creates new opportunities. New stars mean new planetary systems. If any of those planets are in the right place with the right conditions, they could potentially develop life. So while the merger might be dangerous for existing life, it also seeds the galaxy with new possibilities. The starburst regions would be incredible to observe. Imagine vast nebulas, glowing in brilliant reds and blues, lit from within by clusters of newborn stars. Some of these nebulas would span hundreds of light years, containing enough material to make millions of stars. They'd be visible from across the galaxy, beacons of creation amid the chaos of the merger. Within these nebulas, you'd see dark pillars and columns, regions where dense gas is resisting the erosive effects of stellar winds and radiation. These pillars are stellar nurseries, places where the next generation of stars is still forming. They're similar to the famous pillars of creation in the Eagle Nebula, but much larger and more numerous. Let's dig into what's actually happening inside these star-forming regions, because it's a beautiful example of how the universe creates complexity from simplicity. When two gas clouds collide during the merger, they don't just bounce off each other, they interpenetrate, mixing together. The collision compresses the gas, increasing its density. When gas gets dense enough and cold enough, gravity can pull it together into clumps. These clumps continue to collapse, getting denser and hotter until eventually the core becomes hot enough for nuclear fusion to ignite. That's when a star is born. But not all of the gas becomes stars. A lot of it gets heated by the newly formed stars and blown away. This is where stellar feedback comes in. The radiation and winds from hot young stars heats the surrounding gas, creating pressure that resists further collapse. This is why star formation is relatively inefficient. Only a small fraction of the available gas actually ends up in stars. The composition of the gas matters too. The gas in both the Milky Way and Andromeda has been enriched with heavy elements from billions of years of stellar evolution. Every star that's lived and died has added to this enrichment. Supernovas are particularly important because they create elements heavier than iron and scatter them into space. This enriched gas is what allows rocky planets to form. In the early universe, shortly after the Big Bang, the only elements that existed were hydrogen, helium, and trace amounts of lithium. You can't make planets out of just those elements. You need heavier elements: carbon, oxygen, silicon, iron. These elements are created in stars and scattered by supernovas. By the time of the merger, both galaxies have been making stars for 13 billion years. The gas in both galaxies is thoroughly enriched with heavy elements. Any new stars that form during the merger will have this enriched composition, and they'll be able to form rocky planets just like Earth. In fact, the composition might be even richer than what we have today. The burst of supernovas during the starburst will inject fresh batches of heavy elements into the gas. The next generation of stars will incorporate this material, becoming even more metal-rich than current stars. This has implications for planet formation. More metals means more rocky material available to build planets. It might also mean larger rocky planets or more of them. The planetary systems that form during and after the merger could be quite different from the systems we see today. After several passages, each one less energetic than the last, the two galaxies finally settle down. They no longer have enough energy to swing apart again. Instead, they're locked together, slowly mixing and stirring as they spiral toward a common center. This final phase takes several 100 million years. The two dense cores sink toward each other through a sea of stars, losing energy through dynamical friction. Eventually, they merge at the center, and the new galaxy reaches a state of equilibrium. What emerges is no longer the Milky Way or Andromeda. It's a new galaxy, sometimes playfully called Milkomeda or Milkdromeda. It's an elliptical galaxy, meaning it has no spiral arms, no disk structure, just a roughly spherical collection of stars. The stars orbit in random directions rather than all moving in the same plane. There's little gas left for star formation because most of it was either consumed during the starburst or heated and blown out of the galaxy by supernova explosions. The new galaxy is bigger than either of the original galaxies. It contains all the stars from both the Milky Way and Andromeda, somewhere around 1 trillion stars or more. Its size is harder to define because elliptical galaxies don't have sharp edges, but it probably extends for a few 100,000 light-years. At the center sits the merged supermassive black hole, weighing around 100 million solar masses. It's now the gravitational anchor of the new galaxy, and all trillion stars orbit around it, though from such large distances that its gravitational influence on any individual star is negligible. After several passages, each one less energetic than the last, the two galaxies finally settle down. They no longer have enough energy to swing apart again. Instead, they're locked together, slowly mixing and stirring as they spiral toward a common center. This final phase takes several 100 million years. The two dense cores sink toward each other through a sea of stars, losing energy through dynamical friction. Eventually, they merge at the center, and the new galaxy reaches a state of equilibrium. What emerges is no longer the Milky Way or Andromeda. It's a new galaxy, sometimes playfully called Milkomeda or Milkdromeda. It's an elliptical galaxy, meaning it has no spiral arms, no disk structure, just a roughly spherical collection of stars. The stars orbit in random directions rather than all moving in the same plane. There's little gas left for star formation because most of it was either consumed during the starburst or heated and blown out of the galaxy by supernova explosions. The new galaxy is bigger than either of the original galaxies. It contains all the stars from both the Milky Way and Andromeda, somewhere around 1 trillion stars or more. Its size is harder to define because elliptical galaxies don't have sharp edges, but it probably extends for a few 100,000 light-years. At the center sits the merged supermassive black hole, weighing around 100 million solar masses. It's now the gravitational anchor of the new galaxy, and all trillion stars orbit around it, though from such large distances that its gravitational influence on any individual star is negligible. The night sky, viewed from anywhere in this new galaxy, would look very different from what we see today. There would be no Milky Way band crossing the sky because we're no longer in a disk. Instead, the sky would be more uniformly filled with stars, though still with variations in density depending on where you are in the galaxy. If you're near the center, in the dense bulge region, the sky would be crowded with stars, many of them old and reddish. If you're in the outer halo, stars would be more sparse, and the main feature would be the glow from the distant central regions. And there would be far fewer young blue stars than there were during the merger. Without much gas left, star formation drops to very low levels. The galaxy becomes dominated by old, long-lived stars, slowly evolving and eventually dying without being replaced. Over tens of billions of years, Milkomeda will gradually fade as its stars burn out one by one. The shape of the new galaxy would be roughly ellipsoidal, possibly with some rotation, but nothing like the organized rotation of the original spirals. There might be some residual structure, shells and ripples in the distribution of stars, echoes of the merger that will persist for billions of years. But the dominant feature would be the smooth, roughly spherical distribution of old stars. Elliptical galaxies are common in the universe, especially in galaxy clusters. Most of them probably form through mergers, just like Milky Way will. They're the end state of spiral galaxy evolution, at least in regions where mergers are common. Throughout this entire story, I've mentioned Earth almost as an afterthought. That's because, from the galaxy's perspective, Earth is completely insignificant. It's one tiny planet orbiting one ordinary star among hundreds of billions. The merger doesn't care about Earth any more than an earthquake cares about a specific grain of sand. But for us, obviously, Earth is important. So what actually happens to it? The first thing to understand is that long before the galaxies collide, Earth will already be uninhabitable. The Sun is slowly getting brighter as it ages, and in about 1 billion years, maybe a bit more, Earth will be too hot for liquid water to exist on the surface. The oceans will evaporate, the greenhouse effect will run away, and Earth will become something like Venus, a scorched, dry planet with a thick atmosphere and surface temperatures hot enough to melt lead. This happens long before Andromeda arrives. So by the time the merger begins, Earth is already dead, at least as a habitat for life as we know it. Any intelligent life that originated on Earth will either be extinct or will have moved elsewhere, maybe to Mars after terraforming it, or to habitats in the outer solar system, or to other star systems entirely. But let's assume Earth still exists as a physical object, and ask what happens to it during the merger. The most likely answer is not much. The Sun will continue to orbit within the new galaxy, following whatever path the gravitational chaos of the merger puts it on. Earth will continue to orbit the Sun, because the forces involved in the merger, while enormous on galactic scales, are too weak and too gradual to significantly affect the orbits of planets around their stars. There is a small chance of a close encounter with another star. If another star passes within a light year or so of the Sun, it could potentially disrupt the orbits of the outer planets. Pluto might get ejected, or Neptune might get knocked into a different orbit. But the inner planets, including Earth, are held much more tightly by the Sun's gravity and would probably be unaffected. There's an even smaller chance of a very close encounter, one that brings another star within the solar system itself, inside the orbit of the outer planets. This could be catastrophic, potentially stripping away planets or sending them into new orbits. But the chances of this happening are extremely low, well under 1%, even during the most chaotic phases of the merger. The Sun itself will still be a star at this point, though an old one. About 4 billion years from now, the Sun will be nearing the end of its main sequence lifetime. It's currently about halfway through its 10 billion year lifespan as a stable, hydrogen-fusing star. By the time Andromeda arrives, it will be perhaps 8 to 8.5 billion years old, getting close to the point where it runs out of hydrogen in its core. Within another billion years or so after the merger, the Sun will begin its transformation into a red giant. Its core will contract and heat up, while its outer layers will expand enormously. It will swell to perhaps 100 times its current diameter, large enough to swallow Mercury and Venus, and possibly Earth as well. Even if Earth isn't directly consumed, it will be heated to the point where the surface melts. This fate awaits the Sun, regardless of the merger. The collision with Andromeda doesn't change the Sun's internal evolution. It's a star of a certain mass, and stars of that mass always follow the same basic life cycle. The merger might change where the Sun ends up in the galaxy, and it might slightly affect the environment around the Sun, but it doesn't change the Sun's destiny. So the final answer is that Earth, if it physically survives, will end up somewhere in the Milky Way galaxy, still orbiting an aging Sun that's about to become a red giant. By that time, Earth will have been lifeless for billions of years, its oceans long gone, its atmosphere stripped or transformed beyond recognition. The galaxy around it will have changed completely, but Earth itself will have been much more affected by the simple passage of time and the aging of its star than by the dramatic merger happening around it. Let's briefly consider the fate of the other planets in our solar system, because they're all part of this story too. Mercury and Venus are doomed regardless of the merger. When the Sun becomes a red giant, both planets will almost certainly be engulfed and vaporized. They're close enough to the Sun that even the expansion of its outer layers will reach them. As the Sun swells, its outer atmosphere will extend past their orbits, and the atmospheric drag will cause them to spiral inward and be consumed. Mars, being farther out, will probably survive the Sun's red giant phase physically, though it will be heated significantly. Interestingly, when the Sun expands, Mars might actually enter the habitable zone for a brief period, geologically speaking. Its surface ice could melt, and if there's any atmosphere left, it might become briefly hospitable. But this would only last a few 100 million years before the Sun sheds its outer layers and shrinks down to a white dwarf, at which point Mars would freeze again. The gas giants, Jupiter, Saturn, Uranus, and Neptune, are far enough from the Sun that they'll survive the red giant phase with relatively little change. They might lose some of their outer atmospheres, heated and blown away by the Sun's increased luminosity, but their cores will remain intact. Their many moons might have more interesting fates. Some of them, heated by the brighter Sun, might temporarily become more hospitable, though hospitable is relative when you're talking about a moon that's mostly ice. Europa and Enceladus, moons with subsurface oceans today, might see those oceans become more active. The increased solar heating could drive more geological activity, creating more hydrothermal vents and potentially more habitable environments. If any life exists in those oceans today, it might actually benefit from the increased energy input. But this would be temporary. Once the Sun becomes a white dwarf, cooling and dimming over billions of years, these moons would freeze solid again. The brief window of increased habitability would close. The outer solar system, including the Kuiper belt and the Oort cloud, will remain largely unchanged by the Sun's evolution. These regions are so far from the Sun that even a 100-fold increase in solar luminosity barely affects them. The comets and ice bodies out there will continue their slow orbits, largely oblivious to the changes happening closer in. But the merger could affect these outer regions. The gravitational chaos of the merger will send ripples through the galaxy, and some of those ripples will reach the solar system. The Oort cloud, which is only very loosely bound to the Sun, could be partially stripped away. Some comets might be sent into the inner solar system, increasing the impact rate on planets. Others might be lost to interstellar space entirely. If the Sun gets ejected from the galaxy, the entire solar system goes with it. Planets, moons, asteroids, comets, and all. It becomes a rogue solar system, wandering through intergalactic space. From the outer planets, the night sky would become incredibly dark. The Sun would still shine, still providing light and heat to its planets, but the stars would disappear. The galaxy, now distant, would be visible as a bright smudge, but there would be no more constellations, no more Milky Way band, just darkness. This is an unlikely fate, but it's possible. Most stars remain gravitationally bound to the new galaxy, but a small percentage don't. Estimates suggest anywhere from 1 to 10% of stars might be ejected during a major merger. If we're unlucky, we could be among them. Now let's ask a more philosophical question. If intelligent life still exists somewhere in the solar system, or in the galaxy generally, what would it be like to live through the merger? First, remember that this entire process takes billions of years. No individual organism, not even an individual civilization, would experience the whole thing. You'd need a continuous chain of civilizations, each one building on the knowledge of the previous to maintain awareness of what's happening over such vast timescales. But let's imagine such a civilization exists. Maybe it's an extremely long-lived spacefaring society, or maybe it's a series of successor civilizations that inherit records from their predecessors. What would they observe? In the early stages, millions of years before first contact, they'd see Andromeda growing larger in the sky. Their astronomers would be able to predict the collision with increasing accuracy. They'd map the approaching galaxy in detail, identify its structure, locate its supermassive black hole, estimate the timing of first contact. They'd have centuries or millennia of advance warning. This would give them time to prepare, to move populations away from dangerous regions, to build shelters or habitats that could withstand increased radiation. A sufficiently advanced civilization could essentially evacuate entire regions of the galaxy that were expected to be particularly affected. As the galaxies draw closer, they'd see the tidal distortions begin. Long streams of stars pulled from each galaxy would become visible. The rate of supernova explosions in both galaxies would increase as the starburst began. The night sky would gradually brighten and become more chaotic. During the actual passages, assuming they had telescopes and sensors scattered throughout the region, they'd observe vast structures in motion, spiral arms being torn apart, gas clouds colliding and igniting into new star-forming regions. The galactic cores approaching each other. It would be a spectacle on an unimaginable scale, playing out over millions of years but observable in its entirety through records and predictions. They might even detect the gravitational waves from the merging supermassive black holes if they had advanced enough technology. This would be a huge scientific prize, direct observation of one of the most energetic events in the universe. The gravitational wave signal would provide detailed information about the black hole's masses, spins, and orbital dynamics. But what about the dangers? Would a civilization living through the merger be in peril? The answer depends on where they are and what resources they have. If they're confined to a single planet, they're vulnerable to environmental changes. An increased rate of supernova explosions could bathe their planet in harmful radiation. A close encounter with another star could disrupt their planet's orbit or cause catastrophic comet impacts. Climate change from varying stellar radiation could make their world uninhabitable. But if they're a spacefaring civilization with the ability to move between star systems or build habitats in space, they can avoid most of these dangers. They could simply move away from dangerous regions and relocate to safer areas. A civilization with the ability to travel between stars wouldn't be tied to any one location. They could ride out the merger by staying in the safest regions and avoiding the most chaotic areas. In fact, a sufficiently advanced civilization might even benefit from the merger. The starburst creates new stars, new planetary systems, new real estate for expansion. The increased density of stars in some regions means shorter travel times between systems. And the dramatic events provide unprecedented opportunities for scientific observation. Imagine being able to study a galaxy merger from the inside, with instruments and observers distributed throughout both galaxies. You could map the gravitational fields in real time, observe the formation of new stars up close, track the motion of individual star systems as they respond to the gravitational chaos. It would be the ultimate natural laboratory for studying galactic dynamics. From a very long-term perspective, civilizations that survive the merger would inherit a new galaxy with its own characteristics and challenges. Milky would be an elliptical galaxy, meaning no spiral arms, no organized disk structure. This might make navigation more complicated since you can't use spiral arms as landmarks. But it would also mean a more uniform distribution of stars, fewer regions of extreme density or emptiness. Star formation in Milky would be much lower than in either the Milky Way or Andromeda today, because most of the gas would have been used up during the starburst or heated and expelled from the galaxy. This means fewer new stars, fewer new planetary systems. Existing civilizations might find themselves in a slowly dying galaxy with no new stars to replace the old ones as they burn out. But this is a problem for the very distant future, tens of billions of years away. In the shorter term, say the next few billion years after the merger completes, there would still be plenty of stars, plenty of resources, plenty of opportunities for life and civilization. A civilization that successfully navigates the merger would have demonstrated remarkable resilience and adaptability. They'd need the technology to monitor and predict galactic dynamics, the infrastructure to move populations when necessary, and the social cohesion to maintain continuity across millions of years. It would be an incredible achievement, a testament to the power of intelligence and cooperation on cosmic scales. Let's change perspective for a moment and imagine we're observing this merger from outside, from another galaxy in the local group. What would we see? From a distance, the merger of the Milky Way and Andromeda would be visible as two spiral galaxies gradually approaching each other. At first, they'd be distinct, each with its own structure. As they drew closer, tidal features would become apparent. Long tails and bridges of stars stretching between the galaxies. During the first passage, the galaxies would overlap, their structures blending together in a complex, chaotic mix. Then they'd separate again, each now more distorted than before. With each subsequent passage, the structures would become more disrupted, the tidal features more prominent, the starburst brighter. The whole process would be like watching two drops of water merge in slow motion. They approach, touch, merge partially, separate, come back together, separate again, each time mixing more thoroughly, until finally they form a single combined drop. From an astronomer's perspective, this would be an incredible opportunity. Galaxy mergers are common in the universe. We see them happening all the time at various stages. But most of them are millions or billions of light years away. The merger of the Milky Way and Andromeda is happening right in our cosmic backyard, close enough to study in exquisite detail. If there are any astronomers in the local group's smaller galaxies, like the Triangulum Galaxy or the Magellanic Clouds, they'll have a front-row seat to one of the most spectacular shows in the universe. They'll be able to track individual stars, observe the starburst regions in detail, measure the gravitational waves from the merging black holes. It would be the equivalent of having the Super Bowl played in your backyard instead of on TV from 1,000 miles away. Let's change perspective for a moment and imagine we're observing this merger from outside, from another galaxy in the local group. What would we see? From a distance, the merger of the Milky Way and Andromeda would be visible as two spiral galaxies gradually approaching each other. At first, they'd be distinct, each with its own structure. As they drew closer, tidal features would become apparent. Long tails and bridges of stars stretching between the galaxies. During the first passage, the galaxies would overlap, their structures blending together in a complex, chaotic mix. Then they'd separate again, each now more distorted than before. With each subsequent passage, the structures would become more disrupted, the tidal features more prominent, the starburst brighter. The whole process would be like watching two drops of water merge in slow motion. They approach, touch, merge partially, separate, come back together, separate again, each time mixing more thoroughly until finally they form a single combined drop. From an astronomer's perspective, this would be an incredible opportunity. Galaxy mergers are common in the universe. We see them happening all the time at various stages. But most of them are millions or billions of light years away. The merger of the Milky Way and Andromeda is happening right in our cosmic backyard, close enough to study in exquisite detail. If there are any astronomers in the local group's smaller galaxies, like the Triangulum Galaxy or the Magellanic Clouds, they'll have a front-row seat to one of the most spectacular shows in the universe. They'll be able to track individual stars, observe the starburst regions in detail, measure the gravitational waves from the merging black holes. It would be the equivalent of having the Super Bowl played in your backyard instead of on TV from 1,000 miles away. But they might also be nervous because the merger of the two largest galaxies in the local group will affect everyone. The gravitational influence of the merger will be felt throughout the entire local group. Smaller galaxies might have their orbits disturbed. Some might even be pulled in and absorbed by the growing Milky Way galaxy. This is actually the eventual fate of most of the local group. Gravity is always pulling, always drawing things together. Over tens of billions of years, most of the galaxies in the local group will likely merge into a single giant galaxy. The merger of the Milky Way and Andromeda is just the first and most dramatic step in that process. The Triangulum Galaxy, for instance, is already gravitationally bound to the Andromeda system. It's likely to merge with Andromeda either before or shortly after the Milky Way collision. The final result might not be just Milky Way, but an even larger galaxy incorporating Triangulum as well. The Magellanic Clouds, currently orbiting the Milky Way, will probably be consumed long before the Andromeda merger. They're already losing gas to the Milky Way's gravity, creating the Magellanic Stream. Within a few billion years, they'll likely fall into the Milky Way entirely, adding their stars and gas to our galaxy before Andromeda arrives. So an outside observer would see not just two galaxies merging, but an entire galaxy group coalescing into a single massive system. It's a process of cosmic consolidation, gravity pulling everything together into larger and larger structures. We haven't talked much about dark matter yet, but it plays a crucial role in the merger, even though we can't see it directly. Dark matter is the mysterious stuff that makes up about 85% of the matter in the universe. We can't see it because it doesn't emit, absorb, or reflect light. We know it exists because of its gravitational effects. Galaxies rotate too fast to be held together by just the visible matter. There must be additional invisible mass providing extra gravity. Galaxy clusters are bound together by much more mass than we can see. And the way light bends around massive objects through gravitational lensing tells us there's more mass present than the visible matter accounts for. Each galaxy, including the Milky Way and Andromeda, is embedded in a massive halo of dark matter. This halo extends far beyond the visible disk, out to perhaps 10 times the radius of the visible galaxy. And it contains several times more mass than all the stars, gas, and dust combined. When two galaxies merge, their dark matter halos merge too. In fact, the dark matter halos merge first, before the visible parts of the galaxies even touch. This is because the dark matter halos are so much larger. By the time the visible disks start to overlap, the dark matter halos have already interpenetrated and begun to mix. The merger of the dark matter halos is important because it's the dark matter's gravity that does most of the work in pulling the galaxies together. The visible matter, the stars and gas, follow along, responding to the combined gravitational field of both dark matter halos. But dark matter merges differently than normal matter. When gas clouds collide, they interact, they compress and heat up, they radiate energy. Dark matter doesn't do any of that. Dark matter particles pass right through each other without interacting, except through gravity. So when two dark matter halos merge, they don't crash together violently. They just gradually mix, their particles interleaving like two clouds of gnats passing through each other. This means the dark matter merger is actually smoother and less dramatic than the visible merger. While the stars and gas are being thrown into chaos, with tidal tails and starbursts and everything we've talked about, the dark matter just quietly blends together into a single larger halo. The final merged galaxy, Milky Way, will sit within a dark matter halo that contains the combined mass of the Milky Way's and Andromeda's halos. This halo will be even larger than either of the original halos, extending perhaps 1,000,000 light-years or more from the galaxy's center. This dark matter halo is what will hold Milky Way together. The visible galaxy, all the stars and gas, only makes up about 15% of the total mass. The rest is dark matter, providing the gravity that keeps everything bound. Without the dark matter halo, Milky Way would fly apart, unable to hold itself together against its own rotation. The structure of the dark matter halo affects how the merger proceeds. Computer simulations show that the distribution of dark matter influences the tidal forces, the timing of the passages, and the final structure of the merged galaxy. A more concentrated dark matter halo produces stronger tidal forces. A more extended halo results in a gentler merger. Understanding dark matter is one of the biggest challenges in modern physics. We know it exists, we can measure its effects, but we don't know what it's made of. The leading candidates are exotic particles that barely interact with normal matter, passing through the Earth and through our bodies every second without us noticing. Experiments around the world are trying to detect these particles directly, but so far, none have succeeded. The merger of the Milky Way and Andromeda provides another way to study dark matter. By observing how the galaxies move and how the tidal tails form, astronomers can infer the distribution and properties of the dark matter halos. This information helps constrain theories about what dark matter might be. Let's jump way ahead now, billions of years beyond the merger. What's the long-term future of Milky Way? In the short term, meaning the first few billion years after the merger, Milky Way will be a relatively bright, active galaxy. There will still be gas left over from the merger, still some star formation happening, though at a lower rate than during the starburst. The galaxy will gradually settle down, its stars' orbits becoming more regular, its structure more stable. But over longer timescales, tens of billions of years, Milky Way will slowly fade. Star formation will continue to decline as the remaining gas is used up or ejected from the galaxy. The massive stars born during the merger will have long since died, leaving behind neutron stars or black holes. The medium-mass stars will have evolved into white dwarfs. Eventually, only the smallest, longest-lived red dwarf stars will remain, along with the remnants of all the larger stars. Red dwarfs can live for trillions of years. They're so small and burn their fuel so slowly that even the oldest red dwarfs in the universe today, born shortly after the Big Bang, are still in their infancy. It will take hundreds of billions of years, possibly over 1,000,000,000 years, for the first red dwarfs to finally run out of hydrogen and die. So Milky Way will continue to exist as a galaxy for an enormously long time, but it will gradually become darker and darker as its stars burn out. By 100 billion years from now, most of the stars will be dead, and the galaxy will be filled with white dwarfs, neutron stars, and black holes. The only light will come from the dwindling population of red dwarfs and the occasional flare when two white dwarfs collide or a star gets torn apart by the central black hole. Eventually, even the red dwarfs will die, and Milky Way will become a dark galaxy, a vast collection of stellar remnants bound together by gravity but emitting almost no light. The black holes will continue to exist, slowly evaporating through Hawking radiation over timescales of 10 to the power of 100 years or more. The white dwarfs and neutron stars will gradually cool, eventually reaching the ambient temperature of the universe. This is the ultimate fate of all galaxies in the universe, not just Milky Way. The universe is currently in what might be called its stelliferous era, the age of stars. This era began a few 100 million years after the Big Bang, when the first stars formed, and it will continue for trillions of years into the future. But it won't last forever. Eventually, star formation will cease throughout the universe as all the gas is used up, and the stelliferous era will end. After that comes the degenerate era, when the universe is filled with stellar remnants, but no living stars. And after that, over even longer timescales, the black hole era, when even the remnants have decayed and only black holes remain. And finally, the dark era, when even the black holes have evaporated and the universe contains nothing but a thin soup of particles and radiation, slowly spreading out and cooling toward absolute zero. But that's getting far beyond the scope of our story. For our purposes, the important point is that the merger of the Milky Way and Andromeda is part of a natural life cycle of galaxies. Galaxies form, they grow by merging with other galaxies, they form stars, and eventually they fade as their fuel runs out. The merger with Andromeda is a dramatic event in this life cycle, but it's not an ending, it's a transformation. Let's zoom out even further and consider what the merger means in the context of the universe as a whole. The local group, our little cluster of galaxies, is just one of countless groups and clusters scattered throughout the observable universe. Some of these clusters are much larger than the local group. The Virgo cluster, for example, contains over 1,000 galaxies. The Coma cluster contains even more. And these clusters are themselves part of even larger structures called superclusters. Our local group is part of the Virgo supercluster, also called the Laniakea supercluster. It's an enormous structure containing tens of thousands of galaxies spread across hundreds of millions of light years. And Laniakea is just one of millions of superclusters in the observable universe. In the early universe, galaxies were smaller and closer together. Mergers were common. Many of the large galaxies we see today, including the Milky Way and Andromeda, were built up through multiple mergers over billions of years. Each one absorbed smaller galaxies, grew larger, and became more massive. But here's the thing: the universe is expanding. Space itself is stretching, carrying distant galaxies away from each other. This expansion is accelerating, driven by something called dark energy, which is even more mysterious than dark matter. Dark energy is causing the expansion of the universe to speed up, and as a result, distant galaxies are moving away from us faster and faster. Eventually, most galaxies will be moving away from each other so quickly that they'll never merge. The only mergers that will continue to happen are within gravitationally bound groups and clusters, where the mutual gravity is strong enough to overcome the expansion of space. The local group is one of these bound systems. The Milky Way and Andromeda are close enough and massive enough that their mutual gravity has overcome the expansion of the universe. They're falling together, not being carried apart. The same is true for the other galaxies in the local group. But beyond the local group, things are different. The galaxies in the Virgo cluster, for example, are moving away from us due to the expansion of space. We'll never merge with them. In fact, in the very distant future, as the expansion of the universe continues to accelerate, even these relatively nearby galaxies will be carried so far away that they'll disappear from view entirely. Their light will be redshifted to such long wavelengths that it becomes undetectable. Eventually, billions of years from now, Milky will be alone. All the other galaxies beyond the local group will have been carried so far away by the expansion of space that they'll no longer be visible. An astronomer in Milky billions of years from now, looking out at the universe, would see only their own galaxy and a few small satellite galaxies. They might conclude that the universe contains only one galaxy, having no way to detect the billions of other galaxies that exist beyond their cosmic horizon. This is one of the strange consequences of living in an accelerating universe. Future civilizations will have a fundamentally different view of the cosmos than we do. We're actually living in a special time, cosmologically speaking. We can see a large portion of the observable universe. We can detect galaxies billions of light years away. We can observe the cosmic microwave background radiation, the afterglow of the Big Bang itself. Future observers won't have these advantages. So in a way, the merger of the Milky Way and Andromeda is one of the last great mergers that will ever be visible to observers in our region of space. After Milky forms, there will be little left to merge with. The local group will have consolidated into one or two large galaxies, and everything else will be unreachably distant. Finally, let's bring this back to a human scale and ask what all of this means for us, here and now. On a practical level, it means nothing. The merger is 4 billion years away. Humanity, in any form we'd recognize, will almost certainly be long gone by then. Either we'll have gone extinct, or we'll have evolved or technologically transformed ourselves into something completely different, or we'll have spread out across the galaxy and diversified into multiple separate species or civilizations. But on a philosophical level, the merger tells us something important about our place in the universe. We're not living in a static cosmos. We're living in a dynamic, evolving universe where everything is in motion, everything is changing. Galaxies merge, stars form and die, planets come into existence and eventually are destroyed. The universe is 13.8 billion years old, and it will continue to evolve for trillions of years into the future. The merger of the Milky Way and Andromeda is just one event in that long history. It's dramatic from our perspective because it involves our home galaxy. But from the universe's perspective, it's routine. Galaxies merge all the time. This realization can be humbling. We're tiny, fleeting creatures on a small planet orbiting an ordinary star in a galaxy that's about to be completely transformed. In the grand scheme of things, we're barely a blip. But it can also be empowering, because we're part of this story. We're made of atoms that were forged in stars, scattered by supernovas, and eventually assembled into planets and life. We're the universe becoming conscious of itself, able to observe and understand the processes that created us. And we're living at a unique moment in cosmic history. We can see the universe in its current state with billions of galaxies visible, with the cosmic microwave background still detectable. We can predict the merger of our galaxy with Andromeda. We can understand dark matter and dark energy, even if we can't directly observe them. We can trace the evolution of the universe from the Big Bang to the present and project forward to the distant future. We've talked a lot about what happens to stars and galaxies, but let's zoom in even further and think about what happens to planetary systems during the merger. After all, stars don't exist in isolation. Many of them, possibly most of them, have planets orbiting around them. The good news is that planetary systems are remarkably stable. The gravitational bond between a planet and its star is much stronger than any external forces the merger will produce. Think about our own solar system. The Sun's gravity holds Earth in its orbit with a force that's enormously stronger than the gravitational pull from even the nearest stars. Proxima Centauri, our closest stellar neighbor, is 4 light-years away, and its gravitational influence on Earth is essentially zero. During the merger, even as stars pass relatively close to each other by galactic standards, they're still separated by distances measured in light years, or at least light months. At these distances, the gravitational pull on planets is negligible. Earth will continue to orbit the Sun, Mars will continue in its path, Jupiter will keep its moons. The architecture of the solar system will remain intact. However, there are some subtle effects worth considering. While direct disruption of planetary orbits is unlikely, the changing gravitational environment can have long-term effects on the outer reaches of planetary systems. Remember the Oort cloud we discussed earlier, that vast shell of comets surrounding the solar system at a distance of about 1 light-year. This region is so far from the Sun that the comets there are only barely held by the Sun's gravity. During the merger, as other stars pass within a few light-years, their gravity can nudge these comets, changing their orbits. Some comets might be pulled away from the Sun entirely, stolen by passing stars. Others might be knocked into new orbits that send them plunging into the inner solar system, increasing the rate of comet impacts on the planets. This effect could last for millions of years as the merger unfolds, creating a period of enhanced bombardment. For life on any planet, this could be significant. Large comet impacts can cause mass extinctions, dramatically alter climates, and reshape the surface of worlds. Earth has experienced major impacts in its past, most famously the impact that killed the dinosaurs 65 million years ago. During the merger, the frequency of such impacts might increase substantially. But there's also a positive side to this story. Comets contain water and organic compounds, the building blocks of life. Increased comet delivery to planets could actually seed them with the ingredients necessary for life to begin. In the early solar system, it's thought that comets delivered much of Earth's water and possibly some of the organic molecules that eventually led to life. During the merger, this process could repeat on countless worlds throughout both galaxies. There's another potential effect on planetary systems related to the starburst we discussed. When massive stars form and later explode as supernovas, they release intense radiation. If a supernova occurs within about 30 light-years of a planetary system, it could be hazardous to life on those planets. The radiation could strip away parts of the atmosphere, damage the ozone layer if one exists, and expose the surface to harmful cosmic rays. The increased rate of star formation during the merger means more massive stars being born, which means more supernovas later. This could create regions of the merging galaxies that are temporarily more hazardous for life. Planets in or near starburst regions might experience extinction events triggered by nearby supernova explosions. On the other hand, not all effects are negative. The enrichment of the interstellar medium with heavy elements from supernovas means that new planetary systems forming during and after the merger will have access to a richer mix of elements. These planets might have more thorium and uranium for radioactive heating of their interiors, more iron for magnetic field generation, more carbon and nitrogen and oxygen for complex chemistry. They might be better suited for developing life than planets that formed earlier with less metal enrichment. There's also the fascinating question of rogue planets. These are planets that have been ejected from their parent star systems, either through gravitational interactions with other planets or with passing stars. They wander through interstellar space, no longer orbiting any star, heated only by their internal heat and the faint glow of the cosmic microwave background. During the merger, the chaotic gravitational environment will likely create many rogue planets. A close encounter between two stars might eject planets from one or both systems. These planets become interstellar wanderers, drifting through the galaxy on their own. Some estimates suggest there might already be as many rogue planets as there are stars, and the merger could substantially increase this population. For any life on a rogue planet, assuming life could exist in such a cold, dark environment, the merger would be an interesting time. The planet would pass through regions of increased stellar density, occasionally coming close to stars or other planets. There might even be rare occasions when a rogue planet gets captured by a new star, joining a new planetary system entirely different from the one it was born in. The merger might also create planetary systems with very different architectures from what we're used to. During close stellar encounters, while complete disruption is rare, subtle gravitational perturbations can occur. A planet on an initially circular orbit might be nudged into a more elliptical orbit. Multiple planets in a system might have their orbital resonances disrupted, leading to instabilities that play out over millions of years. Some planetary systems might even capture planets from other systems during close encounters. Imagine two stars passing within half a light year of each other. A planet on a wide orbit around one star might be pulled away by the gravity of the other star, switching allegiance mid-flight. This would create planetary systems with a mix of planets from different origins, possibly with very different compositions and histories. Let's get into the nitty-gritty of what happens when stars pass close to each other during the merger. We've said that actual collisions are rare, but what exactly happens during a close encounter? The key concept is gravitational scattering. When two stars approach each other, they don't just pass by unaffected, they exchange energy and momentum through gravity, altering each other's trajectories. It's similar to what happens when two billiard balls collide, except the stars don't physically touch. They interact through gravity alone, and the collision happens over months or years as the stars approach, reach their closest point, and then recede. The outcome of a stellar encounter depends on several factors: how close the stars get, how fast they're moving relative to each other, and their masses. Let's consider some scenarios. If two stars pass within a few light weeks of each other while moving at typical galactic velocities, which are hundreds of kilometers per second, they'll exchange some energy and momentum. One star might be sped up slightly while the other is slowed down. Their directions of motion will change, bending their paths through space. This is called gravitational deflection, and it's the primary mechanism by which stars' orbits get randomized during a galaxy merger. Now, if the stars happen to be moving slowly relative to each other, and they pass very close, something more interesting can happen. They might temporarily become gravitationally bound to each other, forming a binary star system. This would be a loose binary, with the two stars orbiting each other at a distance of light months or light years, but it would be stable over millions of years. However, if a third star comes along and interacts with this binary, the system becomes unstable. Three-body gravitational interactions are chaotic and unpredictable. The most common outcome is that one star gets ejected at high speed, becoming what's called a hypervelocity star, while the other two form a tighter binary. This process, called binary hardening through three-body interactions, is one way that close binary star systems form. Hypervelocity stars are fascinating objects. These are stars moving so fast that they can escape the galaxy's gravity entirely. They've been accelerated to speeds of hundreds or even thousands of kilometers per second, fast enough to reach escape velocity. We've detected several hypervelocity stars in the Milky Way, and they're thought to be created by interactions with the supermassive black hole at the galactic center, or by binary interactions in dense stellar environments. During the merger, the creation of hypervelocity stars will increase dramatically. Close encounters between stars will be more common, especially during the core passages. Some of these encounters will result in stars being flung out of the galaxy at enormous speeds. These stars, along with any planets they might have, will become intergalactic travelers, leaving the merged galaxy entirely and heading out into the void between galaxies. There's also the question of what happens to existing binary star systems during the merger. Many stars are already in binary or multiple star systems, orbiting each other in stable configurations. During a close encounter with a third star, these systems can be disrupted. The intruder star might pull one component away from the binary, breaking it apart. Or it might join the system, creating a triple star system. Triple star systems are less stable than binaries and often undergo complex gravitational interactions that eventually result in one star being ejected. So the merger might temporarily create many triple systems, which then gradually decay back to binaries plus single stars over millions of years. For very close stellar encounters, within a few light days or light hours, additional effects come into play. At these distances, tidal forces become significant. Just as the moon raises tides on Earth's oceans, a passing star can raise tides on another star. These stellar tides are bulges in the star's outer layers, pulled toward the other star by its gravity. In extreme cases, if the stars are close enough, and at least one of them is an evolved giant star with a very extended envelope, these tidal forces can be disruptive. Material from one star's outer layers might be stripped away and transferred to the other star, or lost into space entirely. This creates what astronomers call a tidal interaction, and it can significantly alter both stars. However, for main sequence stars like our Sun, which are compact and held together strongly by gravity, tidal disruption would require an impossibly close encounter, closer than the radius of the Sun itself. Since such close approaches essentially never happen in galaxy mergers, tidal disruption of normal stars isn't a concern. It only matters for giant stars with extended, loosely bound envelopes. The overall effect of all these stellar encounters is to randomize the orbits of stars in both galaxies. Before the merger, stars in a spiral galaxy move in fairly orderly, circular orbits around the galactic center, all in roughly the same plane. After the merger, stars move in random directions with a mix of orbital shapes from nearly circular to highly elliptical. This randomization is what destroys the spiral structure and creates the elliptical galaxy that results from the merger. While stars pass through each other like ghosts, gas behaves very differently during a galaxy merger. Gas clouds can collide, and when they do, they don't just pass through each other. They crash together, compress, heat up, and create shock waves. This is where much of the drama of the merger happens. Imagine two vast clouds of gas, each spanning hundreds or thousands of light years, each containing millions of solar masses of material, approaching each other at hundreds of kilometers per second. When they meet, it's like two weather systems colliding, creating a cosmic storm of unimaginable scale. At the leading edge of the collision, the gas compresses suddenly. This compression heats the gas, raising its temperature from perhaps 10 or 20 degrees above absolute zero to thousands or even millions of degrees. The heated gas begins to glow, emitting radiation in infrared, optical, and X-ray wavelengths, depending on how hot it gets. Behind the shock front, the compressed gas can become dense enough for gravity to take over. Regions of the gas cloud that reach sufficient density begin to collapse, fragmenting into smaller clumps. These clumps continue to collapse, getting denser and hotter, until eventually nuclear fusion ignites in their cores and stars are born. This is the mechanism behind the starburst we've discussed. It's not just that the merger somehow triggers star formation in general. It's specifically the collision of gas clouds, the compression they create, that pushes gas over the threshold necessary for gravitational collapse and star formation. The efficiency of this process depends on many factors. The speed of the collision matters. If the gas clouds are moving too fast, they might heat up so much that the pressure prevents collapse. If they're moving too slowly, they might not compress enough to trigger star formation. There's a sweet spot where the collision creates just the right conditions for efficient star formation. The density and temperature of the gas clouds also matter. Cold, dense clouds are more likely to form stars when compressed. Hot, diffuse gas is less likely to collapse even when compressed. This means that regions of the galaxies that have a lot of cold molecular gas will experience more intense starbursts than regions with mostly hot, ionized gas. The magnetic fields threading through the gas also play a role. Magnetic fields provide support against gravitational collapse, so strong magnetic fields can suppress star formation even in compressed gas. During the collision, magnetic fields get tangled and amplified, creating a complex electromagnetic environment that affects where and how stars form. There's also turbulence to consider. The collision of gas clouds doesn't create a smooth, uniform compression. It creates turbulent eddies and vortices, regions of chaotic, swirling motion. This turbulence can either help or hinder star formation depending on the details. In some cases, turbulent compression can trigger the collapse of gas clouds. In other cases, turbulent pressure can support clouds against collapse. As the gas clouds collide and star formation begins, the newly formed stars start to affect their environment. The massive stars emit intense ultraviolet radiation that heats the surrounding gas, creating bubbles of hot, ionized gas that glow in characteristic wavelengths. These bubbles expand, pushing gas away, and can trigger further star formation in the compressed shells at their edges. When massive stars explode as supernovas, they inject even more energy into the gas. Each supernova explosion releases as much energy as the Sun will emit over its entire 10-billion-year lifetime, all in a few seconds. This energy heats the gas to millions of degrees, creating vast bubbles of superheated plasma that expand at thousands of kilometers per second. Multiple supernova explosions can create superbubbles, enormous cavities blown in the interstellar medium. These superbubbles can span hundreds of light years and contain gas so hot it glows in X-rays. They're visible as dark regions in images of galaxies, regions where the cold gas has been cleared away by the violence of stellar feedback. Eventually, if enough energy has been injected into the gas, it can escape the galaxy entirely. The gas becomes so hot and is moving so fast that it overcomes the galaxy's gravity and flows out into intergalactic space. This is called a galactic wind, and it's one of the primary ways that galaxies lose their gas and eventually shut down star formation. During the merger, galactic winds are expected to be particularly strong. The intense starburst creates hundreds or thousands of supernova explosions over a relatively short period, a few tens of millions of years. This concentrated energy input drives powerful winds that can expel a significant fraction of the galaxy's gas. This expelled gas doesn't necessarily leave the system permanently. Some of it might fall back onto the galaxy in what's called a galactic fountain. The gas flows out, driven by the energy from supernovas, but it's still gravitationally bound to the galaxy. Eventually, it slows down, stops, and falls back, taking hundreds of millions of years to complete the cycle. The galactic fountain is important because it mixes gas from different parts of the galaxy. Gas enriched with heavy elements from supernova explosions mixes with more pristine gas from the outer regions. When this mixed gas eventually forms new stars, those stars have a more homogeneous composition, more similar to the average composition of the galaxy as a whole. Here's a question worth pondering. Could life not just survive, but actually thrive during the galaxy merger? We've talked a lot about the hazards, the increased radiation, the comet impacts, the disrupted orbits. But are there also opportunities? Consider this. The starburst creates millions of new stars over a relatively short period. Many of these stars will form planetary systems. Within a few 100 million years after the starburst, some of those planetary systems could develop life. So while the merger might be hazardous for existing life, it also creates vast numbers of new potential homes for life. Furthermore, the mixing of gas from different parts of both galaxies means that planetary systems forming during the merger will have access to a thoroughly mixed reservoir of elements. The heavy elements created in the cores of massive stars, scattered by supernova explosions, get mixed throughout the merging system. This could create planets with ideal compositions for developing life, with the right mix of carbon, nitrogen, oxygen, phosphorus, and trace elements. There's also the possibility that life could spread more easily during the merger. The increased density of stars means shorter distances between systems. If life develops the ability to travel between stars, even at sublight speeds, the merger period might be an optimal time for expansion. A civilization could hop from star to star, spreading throughout the merging galaxies. And consider the perspective of any intelligent life that happens to exist during the merger. They would witness one of the most spectacular astronomical events possible. The night sky would be unlike anything we can imagine. Two galaxies colliding, massive stars being born and dying, supernova explosions lighting up the darkness, tidal tails stretching across the heavens. It would be a golden age for astronomy. Such a civilization would also have strong incentives to develop space travel. The changes in the galactic environment, the increased hazards, the knowledge that their region of space might become more dangerous over time, all of this could motivate them to develop the technology to move between star systems, to establish colonies in safer regions, to ensure their survival regardless of what happens to their home world. In a sense, the merger could be a catalyst for the development of advanced civilizations. It creates challenges that must be overcome, but also opportunities for those clever and lucky enough to take advantage of them. The merger is a selection pressure, favoring life and civilizations that are adaptable, resilient, and capable of long-term planning. There's even a scenario, highly speculative but worth considering, where advanced civilizations from both galaxies might contact each other during the merger. As the galaxies interpenetrate, civilizations that were previously separated by millions of light years find themselves much closer. What was once an impossible journey becomes merely difficult. The merger could create opportunities for first contact between civilizations that would never have met otherwise. Of course, this assumes that intelligent life exists in both galaxies, that multiple civilizations develop around the same time, and that they have the technology and inclination to make contact. Those are big assumptions. But if they're true, the merger could be not just a collision of stars and gas, but also a meeting of minds, a collision of civilizations. On a more prosaic level, the merger might actually improve conditions for life in some ways. The mixing of gas and the formation of new stars replenishes the galaxy's stellar population. Without mergers, galaxies would slowly use up their gas, star formation would decline, and the galaxy would gradually fade. The merger keeps the galaxy alive and active, at least for a while longer, creating new stars and new opportunities for life. And remember, all of this plays out over billions of years. That's an enormous amount of time for life to adapt, evolve, and potentially develop intelligence and technology. Life on Earth has gone from single cells to technological civilization in less than 4 billion years. During the merger of the Milky Way and Andromeda, similar evolutionary journeys could occur countless times on countless worlds. So while the merger poses challenges, it also creates possibilities. It's not simply destruction, it's transformation. And with transformation comes the potential for something new, something unexpected, something that couldn't have existed before. That's the nature of change on cosmic scales. It's not good or bad, it's simply different. A new chapter in the ongoing story of matter organizing itself into ever more complex forms. The merger of the Milky Way and Andromeda is more than just an astronomical event. It's a reminder that nothing in the universe is permanent. The galaxies we see today, including our own, are temporary structures. They formed, they evolve, they merge with other galaxies, and eventually they'll fade as their stars burn out. This is the life cycle of galaxies, as natural and inevitable as the life cycle of stars or planets or living things. But within that grand cycle, there's room for incredible complexity and beauty. Stars form from collapsing gas clouds. Planets condense from the disks around young stars. Life emerges from chemistry on some of those planets. Intelligence and civilization develop on some of those worlds, and all of this happens within galaxies that are themselves changing, merging, transforming over billions of years. We're part of that story. We're made from elements created in stars that lived and died billions of years ago. We live on a planet orbiting a star in a galaxy that's in the process of merging with another galaxy. And we have the remarkable ability to understand all of this, to trace the connections, to predict what's coming billions of years into the future. That understanding is one of humanity's greatest achievements. It required centuries of observation, measurement, calculation, and theory. It required telescopes that could see across millions of light years. It required computers that could simulate the complex physics of galaxy mergers. It required thousands of astronomers working over generations, each one building on the work of those who came before. And the result is this story we've told tonight. A story of two galaxies approaching each other, of tidal forces and starbursts, of black holes merging and stars being scattered, of a slow transformation over billions of years that will create a new galaxy unlike either of its parents. It's a story that won't reach its conclusion for 4 billion years. By then, Earth will be uninhabitable. The Sun will be nearing the end of its life. Humanity, if it still exists, will be unrecognizably different. But the merger will proceed according to the laws of physics, indifferent to whether anyone is watching, following the same path that countless other galaxy mergers have followed throughout the history of the universe. Thanks for staying with me through this long journey across space and time. The final hour of the collision may be billions of years away, but in cosmic terms, it's just around the corner. And when it finally arrives, when Andromeda's trillion stars meet the Milky Way's hundreds of billions, it will be one of the most spectacular transformations our corner of the universe has ever seen.